In chapter 6, we were talking about discrete random variables and the probability distributions that go along with them. Specifically, we were interested in the binomial distribution. And now we're going to concentrate in chapter 7 on continuous random variables, specifically the normal distribution, which is the more formal name for bell curves. And I'm typing something in chat here. So, what is a probability distribution that is a uniform probability distribution? And how do we calculate the probabilities there? So let's see here. Let me bring something else up here for a moment. All right. So we see on page 329 at the bottom, it tells us rather than adding up probabilities for a particular value of x, instead, we're going to look at some interval of the number line. It's going to be all those possible values. So we're not just going 1, 2, 3, 4, etc. If you look between 0 and 1, there are infinitely many numbers in there. For example, you could keep cutting things in half and keep getting closer to 0. Or you could be dividing by 10. So you could talk about 0.1, that's close to 0. But 0.01 is even closer. 0.001 is even closer to 0 than any of those. So we're considering infinitely many. And so we'll be talking about the area underneath the curve, between the curve and the horizontal axis, the area over an interval. The overall total area, the total area would have to be 1. It would be like covering 100% of the data in a histogram. And just like a histogram with your frequencies or your relative frequencies, you could have a 0, but everything else is above. So a histogram never went below the horizontal axis. And similarly, when we have a probability density function, or PDF, that cannot go below the horizontal axis. Now here's an example for contrast against the normal distributions and the bell curve graphs that go along with them. Let's see here. It's not showing up. Just a moment. Maybe now it will. There we go. Number 2 on the homework. The graph to the right is a uniform probability density function for a friend who arrives X minutes late. Notice that instead of getting the bell curve, we have the same height all the way along. That's what makes it uniform. So find the probability that the friend is between 25 and 30 minutes late. The graph comes down to 0 at 30, which means that that friend will never be more than 30 minutes late. They're either going to be on time or 10 minutes late or 5 minutes late or 3.5 minutes late. It could be anything between 0 and 30. And I'm going to copy this graph over. Let's see. So 25 to 30 minutes late. Okay. Let's see here. So that value of 1/30th for the height is because we've got a rectangle here with an area that would be the base times the height. So the total area, as we saw at the bottom of page 329, would be 1. And if we're looking for the probability that the friend is 25 to 30 minutes late in part A, that probability is going to be the area of this portion. So we could write this as the probability the friend is between 25 and 30 minutes late. Again, it's not counting. We're not saying 25, 26, 27, etc. It could be any value. It could be 25.1 minutes late, and that friend then would be in that interval. We'd still take the width, which is now 5, times the height of 1/30th, and that would be 5/30 or 1/6, which they're going to want rounded to 3 decimal places. I'll show you that in a moment. So in reality, 1/6 is 0.16 repeating. We're going to round that to 0.167. And let me show you that getting typed in. Make sure that MyLab agrees with that answer. Questions so far? Okay, anybody else? Any questions? Okay, and then in part B, I think they want us working backwards a little bit here. 10% probability that the friend will arrive. Okay, part B, it is 10 a.m. There's a 10% probability that the friend will arrive within how many minutes? Let's see here. 10%. We have a total area under the curve, or in this case, a line of 1. And that's over an interval along the base of 30 minutes. So if I take 10% of 30, I'm getting 3. And double checking, so being 0 minutes late up to 3 minutes late, if I do that just like this, that interval has a width or base of 3, and that'd be times the height of 1/30th. So that's going to be 3/30 or 1/10 which as a decimal is 0.1, or as a percent, 10%. So I'm going to try typing in the answer 3. See if my thinking was correct there. There we go. All right. Questions on that part? Any questions on that part? Okay. So on page 233, we see the empirical rule again. I want to point out something that didn't come up when it was mentioned before. The curve, let me turn off the sharing for just a moment so you can see the board a little bit better. And let's see, I think maybe this one will show up a little bit better. Remember that the peak is above mu on the horizontal axis. And that the bell curve or the normal curve is symmetric. A piece of information that did not come up before is that when you go 1 standard deviation from the mean in either direction, left or right, these points on the curve are called inflection points. And why they're special, if anybody winds up taking any calculus, it comes up maybe halfway to 2/3 of the way through a first semester. The reason we care about it for the normal distribution is that in between, we say that the curve is concave down. It would spill water. If it was something 3-dimensional and it had liquid in it, it would spill it. And then when you go into these tails, to the left tail or the right tail, beyond 1 standard deviation in either direction, then it is concave up and it would hold the liquid. So both here and here, it's concave up. It holds something, you know, if this were a cup, it would be able to hold the water in it. So let's see how we can apply that. Let's see here. Check what I had in my notes first of all. All right, let's see. There we go. So the rest of that is information that we already had about the 68, 95, 99.7% rule within 1, 2, or 3 standard deviations from the mean, and the further breakdown between consecutive intervals there. That percent, if the percents were converted to decimals, typing this in the chat. converted to decimals. And if the total area underneath that curve was 1, then, for example, you would have an area of 0.34 approximately between mu minus sigma and mu itself. That would be the area. And similarly speaking, from mu to mu plus sigma. So we're going to take a look at several other homework questions here. Number 1. All right, let's see here. Number 1. Okay. The total area underneath is 1. So if you go to the right of mu, let's see, I'm trying to make this match up with the image being mirrored. Okay, right. So go to the right from mu, continuing to infinity. Using the symmetry, that's going to be 50%, or as a decimal, 1/2 or 0.5. Questions on that one? Any questions on that part? Okay. Check out number 4. Does that look symmetric to you? Okay. There's more to it. Not only does the normal distribution or the bell curve have to be symmetric and bell-shaped. So you might get something that is, say, skewed left like this one is. Let me turn off the share for a moment again so to show you the board a little better. You could have something that's skewed left, but it's kind of a bell shape. If you don't have both of those facts, symmetric and bell-shaped, then you're not looking at a normal distribution. So what they're looking for in this question, since this one is definitely skewed left, we don't have the bell-shaped and symmetric situation that we should have for a normal distribution. Let me make sure I'm not missing another choice here. So we cannot use a normal distribution. And if you're okay with that one, let's check out number 5. What would you say the value of the mean is based on how they have labeled the horizontal axis? 100. Okay, it's underneath the peak. And furthermore, if you look at where those inflection points are between switching from concave down in between and concave up out in the tails, how much are they moving by? 3 units? Okay. And so that one was also good. I think I had number 6 listed as well. Yes. Now be careful with one like this. We've got mu equals 67 and sigma equals 19. I'm going to switch it over to the document camera a moment. If you're reading the labeling that they have very quickly, you could mistakenly pick the wrong one. For example, let's say I just go to the right. That's close to 20. 67 plus 20 is 87, but since it's only 19, okay, 86. And then if I add another 19 to that, 86 plus 20 is 106. Go down by 1 to 105. And that's actually the first choice that they're showing. And I want you to see why that is the wrong choice. So bringing that back up. Why should it not be choice A? Okay, it should be underneath the peak. And the one that has that is choice C. You've got the 86 to one side. And if you do 67 minus 19, let me go back to the document camera again. 67 minus 19. Well, 67 minus 20 is 47, but I'm subtracting one less, so that should be 48. All I have shown so far is going 1 or 2 standard deviations right and 1 standard deviation to the left. And we should see that 67 underneath the peak. They're only labeling these two to the sides. So that's going to be choice C, I believe. Let's see. Yep, 48, 67 under the peak, and 86 to the right. And notice how those match up with inflection points. I've got one more for now before going back to the notes. I listed number 11. Yes, 11. So 9, 10, and 11. Notice the warning on this one. As the mean increases in part A, since that's just something that's under the peak, let's say you're comparing a few different things that have a normal distribution. Maybe we're talking about the mean height of adult females, and we find that information in Pueblo. We compare that to the mean height of adult females in Colorado Springs and to those in Denver. Let's say we also go out of state to Tulsa, Oklahoma, et cetera, et cetera. And as you make that comparison, say you draw them in different colors on the over the same horizontal axis. Well, the ones that are higher, you're just going to have it shifted along the horizontal axis. And with an increase, it would shift it to the right. So you would see the peak above something that's further right. And that's choice C on this one. If you have a different standard deviation, let me go back to the notes for a moment and show you the well-drawn picture here. If you had a smaller standard deviation, then if you're not changing the mean, if the mean stays the same, so the peak's in the same place, a smaller standard deviation means things are less spread out, and it would take that total area of 1 and compress it. Whereas if the standard deviation's bigger, you still have the peak in the same place. Standard deviation that's bigger means things are more spread out, and you're still supposed to have a total area of 1, so it would spread it out more. So it would become wider. The curve would be lower if it becomes wider, because you need that same, oh, it says decreases. So that was the first one I mentioned. Sorry. A deviation that decreases, it's going to compress horizontally and become steeper. Questions so far? Any questions so far? Okay, let's see what else I had in the notes here. So we use the idea about the area under the uniform distribution to look at the probability of a certain interval occurring, you know, how many minutes late somebody could be. But I want to point out that there are two ways that we could interpret things. Either it's the probability that a randomly selected individual from the population will have the characteristic described by the interval of values, or you could be talking about the proportion of the population with that characteristic that's described by the interval of values. So let's see what's on number 8. There we go. Back to number 8. Suppose that the length of human pregnancies are normally distributed with a mean of 266 days and a standard deviation of 16. And we want to know, I see. Part A. They're telling us that the area to the left in this curve is 0.0263. What that means, since they're shading to the left, they're talking about things less than 235 days. So the proportion of human pregnancies that last less than 235 days is the 0.0263. I'm just paying attention to the direction that they shaded to choose between the less and the more. And using that same information, again, this was less than 235 days. The probability is still 0.0263. Now let's see here. Here, what do they have shaded in between? What two values along the horizontal axis do they have shading above it? Between 280 and 295. Okay. And furthermore, let's see here. Trying to see if they've given us enough information to give a proportion. 16. That's interesting. Okay. Maybe something came up a little earlier than I expected. 280 and 295. And that's in between instead of left or right of that. But trying to figure out what they want us to do since they didn't mark off a probability the way they did up here. So I'm just going to leave that blank and see what we get for warning. That won't let me check it until I type something in there. Okay, so that answer is wrong. Where are you getting the 0.1558 from? There you go. So the area between. Okay. Now, if they did shade everything but that, then you would take 1 minus that. Oh, sorry. 0.1558. Okay. And again, if they had shaded everything else besides that, then we would have picked choice B, and we'd come up with that answer by subtracting 1 minus 0.1558. And the second interpretation, same information. And that's the last part they ask, but I want to add a little bit here. 280, 295, and again, they gave us 0.15. You're right. I thought I had seen the word between, but you're right. I did not. 280, 295, and 0.1558. Okay. Now, before we proceed to anything else, either in the notes or some other question, let me copy that graph down. 280, 295, and then we had a mean of 266. And above my shading, I'm going to write that number of 0.1558. All right. So here's a question where they've asked something like this before when I ask it on a test, and something additional gets asked, and I've seen some interesting answers. Let's say that they take a sample of 100. Since this can both be viewed as a probability and as a proportion of the population, if I simply multiply that number by 100, that would move that 2 to the right. And then in round appropriately, we'd expect 16 out of the 100 pregnancies to last between 280 and 295 days. And by the way, that's in terms of what normal distributions get used for, It shows up a lot in biology, like things like this. If the sample had been of 10,000, times that 0.1558, that 8 is in the 10,000th place. So we'd expect, not accept, expect, here no rounding would be needed. You would expect 1,558 of the pregnancies to be between 280 and 295 days. Forgot to write that up there, between 280 and 295 days. That might show up elsewhere in the homework or on the next section. And I know some questions that I selected for exams last semester that would come up on a question much like this one. And so I wanted to include that. Any questions? Any questions? Okay. And let's also take a look at number 9. Let's see. So here we have somebody apparently golfing and hit 75 golf balls, measured the distance each ball went in yards. And if we were to click this, we would get the data. From that, relative frequencies were calculated. Now, none of these look perfectly symmetric or perfectly bell-shaped, but if we were to take this data and open it up with StatCrunch, and unfortunately it's not showing you that. Give me a moment. So did you see where it gave me the option to open it with StatCrunch? Did you see it when it gave me that option? Yes? Okay. All right. Here's what we have. And we can find out I'm looking under stat. Let's see here. Calculators. That doesn't look helpful. Probably summary stats. Why are there 2 variables? Oh, that's just a number. First attempt, second attempt, third attempt. So we want to find out from the second column, the distances that it's gone, the mean and the standard deviation. So I'm selecting variable 2. Not sure I need to pick anything on this part. Let's see here. See if I can pick these 2 that are separate. Well, we don't need the standard, so we don't need the variance, but so we're getting a mean of 99.85333, which is probably rounded, and a standard deviation of 1.8722247. Let's see here. So, what I'd like to see is, does the data follow the 68, 95, 99.7% rule pretty well? So I'm going to download this also in Excel. Let's see if we can also get our answer about the graph. Okay, that's back. Get a histogram of variable 2. Notice how that peak is pretty close to the 100. So let's see what choices. It's not perfectly symmetric. We're seeing it go like this. There's a little bump of the tail on the left side. Let's close up StatCrunch and whoa. There we were. The one that's showing the peak close to 100 and a little bit of a tail bump, maybe either B or C, but they want relative frequencies, so I'm thinking C. Now, before answering this, I'm going to download this in Excel. There we go. And if you have Excel, you could do the same kind of thing. It's going to save the data to my desktop, so give me a moment. It's taking its time. Okay. We could sort this by the distances. Go to Data and Sort. Select Sort by Distance. I'm going to have it go from smallest to largest. And let me zoom in on this a bit. I'm going to type something in on my calculator and put that under the document camera in a moment here. And then I'll go back to the spreadsheets. I'm finding that the mean, notice I wrote X bar because this was a sample, not the population of every time that he hits a golf ball, but just a sample of 75 attempts, I think it was. Yes, 75 times. So X bar minus S was about 97.98 something, and X bar plus S was about 101.7 something. what we could do, since all of these were measured as whole numbers in meters, we could count up everything that is here we go. I had X bar minus S was 97.98 something. So we'd start with the 98s. And X bar plus S was 101.7 something. So we would go to the 101s because the 102s would be above that. So all of these are fitting the interval X bar minus S to X bar plus S. And real quick, get a count on these. There we go. The 102 would be too far to the right. So that's row 63 was the last entry. And the first entry was row 10. Let me double check the 63. That was attempt 63, the 63rd measurement, but it's in the 66th row. Okay, so what we could do, since subtracting is not the same as counting, I have to add 1 to that. There are 57 attempts that fit that interval, and that's out of 75 attempts. If this is normal, we should have something that's close to 68. And they're probably saying close enough. It's higher, but they're probably going to consider that close enough to say that if we continue that for X bar minus 2S up to X bar plus 2S, we probably have some number close to 95. And then if we did X bar minus 3S to X bar plus 3S, then we'd have about 99.7. So between the graph and what we could find by finding X bar and S and checking what percent of the attempts out of the 75, they're probably saying that this is approximately normal. It's definitely not uniform. It's not like this. So let's see if they agree. Yes. Okay. I'm not going to check that for the other two, but I'm showing you that particularly if you sort the data, I've also shown previously how to sort the data on the TI-84, although I don't think it would be fun to type 75 different scores in. Unless there's a question, let me tell you a little bit about what we'll get into on Wednesday. We're going to wind up using a table that will work after a little bit of calculation for any normal distribution. The mean could be any number at all, and sigma could be any positive number. We've seen this formula before. Although I didn't capitalize Z and X, we've seen X minus mu over sigma to calculate a Z-score. And what that does is it turns whatever normal distribution you have into a standard normal distribution that has a mean of 0 and a standard deviation of 1. And so we're going to use that to answer some questions between using that formula and table 5 in Appendix A. I'll show you where to find that in the book. We're going to answer some questions from biology after we go over using the table when you've already calculated Z. We'll find out these things and then calculate Z and use the table again for a question coming from biology. So I'll leave it at that because getting into these examples, it would take me a minute or so to open up the table 5 anyway. So I'm going to stop here. Any questions? Any questions? Okay. All right. And I'm about to end the meeting. You're welcome. See you Wednesday.